Good morning, doctor. My name is Devinesh Lakitandidabani. My metric card number DE210015. Today I'm going to explain about introduction. The water temperature control system present in this project designed to meet the critical temperature control requirement of modern manufacturing plants. It alternates the LPC1768 microcontroller and calibration software regulate water temperature within a specific rate of 55 to 80 Celsius. Key features of the system include PWM control, plus analog temperature monitoring using the LM35 sensor, and asynchronous series communication for real-time monitoring and data analysis. The system also incorporated data logging capability in store historically temperature. The system also incorporated data logging to store historically temperature data for process optimization and quality control analysis. Overall, this system empower manufacturing plant to achieve consistent product quality process and safe thought previous temperature controller. And for a problem statement for the water temperature control involves the alternation of an LPC 1768 microcontroller to control the temperature of water within range of 55 Celsius to 80 Celsius. The system incorporated both a heater and cooler to achieve this temperature regulation. The LM35 temperature sensor is responsible for measuring the water temperature and the data transmitted to the LPC1768 microcontroller. The system uses LED indicator and computer display to provide real-time feedback on the water temperature. Additionally, a push button is configured as interrupt up to the off the system cooperation when needed. Next, the objective. The primary objective of this project is to develop an efficient temperature control system capable to accurate regulating water temperature in a manufacturing plant within the range of 55 Celsius to 80 Celsius. Key objectives include design a temperature controller algorithm for stabilization, interfacing, and LPC1768 microcontroller with the LM35.
Okay, 39. Hello, my name is Hariputhiran Kannan. My metric number is D210008. Now I'm going to present about methodology. LPC 1768 microcontroller will be used to design a temperature control system for this project. The microcontroller analyzes the data from the sensor and outputs of the result using a computer screen and a LED indicator. To communicate the temperature to the microcontroller as an analog voltage and a thermometer LM35 must be utilized. The microprocessor modifies the heater and cooler model based on the temperature reading to keep the manufacturing plant temperature balanced. Depending on the water's current temperature, the LPC1768 microprocessor will use the information from the LM35 sensor to trigger the heater or cooler in the system. LED lighting will be used as a signal to let people know the current temperature. When water temperature levels exceed the predetermined threshold, the LEDs work by turning on brightly, and when the temperature drops below the minimum temperature levels, they turn on softly. The software that was used to complete this project is Kale UVision 5. Kale is an integrated development environment IDE specified designed for developing and programming embedded systems. It is widely used for ARM-based microcontrollers including LPC1768 in this temperature controller system project. Scale UV Gen 5 offers comprehensive tools and features that facilitate development from writing code to flashing the microcontroller. Next is problem solution. In this control water temperature system shown in figure 1, the KLU Vision software is used to demonstrate the system for the temperature control process by implementing the C program. As table 1 and figure 2 shown below, they are driver specification, the flowchart of the systems respectively. When temperature is at 55 to 80 Celsius, the cooler will be off and the heater will be off. When it's below the 55 Celsius, the cooler will be off, the heater will be on. When it's exceed the 80 degrees Celsius, the cooler will be on and the heater will be off. This is the diverse specification of the water temperature control system.
Good evening, doctor. And my name is Tanesh. My metric number is CE210009. And today I'm going to present about the coding about our assignment 2. And this is the coding for installation, analog digital conversion. Then this brightness LED, interrupt, use serial timer, and we use the LPC1768. Okay. And there are we get three kind of result H, result L, and this is the command and turn off the heater and the cooler while we set up the buttons. So this is LC, and then in our assignment they are given the temperature about 55 degree to 80 degree. So here I set for the 50 set in the volt 0.55, and for the 80 and I set for 0.8. And this is the send data to PC and make result in 12 bit, then extract first 8 bit, extract next 4 bit, and then the installation to analog to digital conversion ADC, and the initial pulse width modulation, and the initialization of GP10 and installation of interrupt. And then here the coding the enable access to diverse lectures, installation of timer, and then setup time delay. And this is our complete coding for this assignment 2. Then I have already run, then there is a zero errors and zero warnings, so it's build the coding. And now I'm going to start the debug. Okay, here is our logic analyzer. To there are our two output, S2 output, and then this port 2, and then this is the ADC converter, and then this general purpose interface output for GP1 and G0 fast interference. Okay, now firstly I'm going to set up the ADC. Okay, now I run this first. Okay, now first of all there is our is now mm, okay, let's take out. Okay. Okay, here is a push button, and this is a push button start and stop reset. And here is the our heater controller, and there is a stop button in our pin 0, and then and here is the temperature setting for the volt analog in analog input. So now we're going to set the below the 55 degrees, so I set for the 5. Then okay, I set 5. Okay, now and we set this pin. mm, okay, there is on, and I'm going to start about I again the push start 2 times. Okay, here is our waveform for this, and then okay, uh, out. Okay, this is the our S2 out and this is the output 2, and then in system analyzer we can see the difference. Okay, this is the output for the S2. Okay, we can see the in logic analyzer, and one there is the 108 and 2. Then here is our waveform in step size. Okay, now I'm going to change the what, so 55 to 80, so maybe we in range of, okay, I keep in 70 degree. So now I again stop the session and I start again, and then here is our output again. So they will change 3 and 100, and our system analyzer also we can see the difference between the previous graph, and here is the difference between the previous we set before 50 and now for the set of the 70. And then you also have the changes for the pin. Okay, now I set above the 80, so I choose 90. So now again I, okay, okay, now again stop and restart the session. Okay, so you can see the pin from here to here though, so so now the output is our will be a bit bigger the step now. uh, now- so you can see the difference obviously. Okay, now the system analyzer, in system analyzer also we can see the difference between the previous and now. So this is the difference between the graph, it's a bit smaller, and the first one is a bit higher, so it decreasing. Okay, that's all for me. Thank you, doctor.
For result analysis, this is the first figure, figure 8.1, the general purpose of input and output for the GPIO 0 and GPIO 1 before starting the system. In this project, the GPIO 0 and GPIO 1 were used to observe the condition of the heater and cooler, whereas the output and the result of the UART2 and PWM were observed by using logic analyzer. The analog digital converter is connected to port 0 bit 23, hence the channel 0 is selected as the analog input. Initially, as shown in figure 8.1, there is no output result at the UART2 and PWM because the start button has not been pressed. From the design coding, the start button is set to port 1 to bit 30 while the stop button is set to port 0 to bit 15. Furthermore, the condition of the cooler and the heater is represented by port 1 bit 17 and port 1 bit 19 respectively. From table 1, the driver specification of the water temperature control system showed that if the binary input is 00, temperature within the body range, both the cooler and heater will be off. On the other hand, if the binary input is 01, the heater will be on while the cooler will be off because the water temperature is less than 55. In contrast, if the temperature exceeds the 80 degrees Celsius, the binary input will show 10, thus the heater will be turned off and the cooler will be turned on. Secondly, figure 8.2, the simulation result for the temperature less than 55 Celsius, which is we use 50 degrees Celsius. Figure 8.2 illustrated the simulation result for temperature less than 55 Celsius. From this figure, it can be found that there was a tick symbol at the port 0 bit 19. This means the heater is turned on when the temperature is less than the valid range. Therefore, the heater is turned on to heat the water temperature. Other than that, the logic analyzer showed the duty cycle at port 2 of the PWM is 50%, which is at the brightness of LED is low, and the data transfer at S2 out is the same as ADDR0 in the ADC, which is 0x0F8.
Hello and good evening. My name is Sailesh Anamati Gopalakrishnan. Street number CE210068. present our group result analysis. So based on figure 8.3, the input analog signal was set to 0.7 70 degrees Celsius, which is within 55 degrees Celsius and 80 degrees Celsius. So there are no thick symbols at the 17-bit and 19-bit of the GPI00. This is because the water temperature stayed moderate, so the heater and cooler did not control the water temperature. Moreover, the duty cycle showed the brightness of the LED in average condition, which is 50% duty cycle, and the data transfer from the system to the computer is 0 times 2AA. So this is our figure 8.3, which is the result. In addition, the case with the water temperature higher than 80 degree was also shown in this program, which is this is the program. While the analog input signal was 90 degrees Celsius at the AINO pin, the simulation result would be same as figure 8.4. It showed that the cooler 17-bit is turned on with a thick symbol at GPI00 to cool down the water temperature. According to the logic analyzer, the LED's brightness is high in an 80% duty cycle. The data transfer computer is 0 times 45D. Finally, an interrupt is set up in the water temperature controller called the stop system. It is controlled manually using a stop button at port 0 bit 15. While this button was pushed, the whole system stopped functioning, as shown in figure 8.5. The figure also shows that the cooler and the heater were turned on, and the logic analyzer stopped displaying the waveform and the data despite an input analog signal. So that is all from me. Thank you. Hello and good evening. My name is Sailesh Analaki Gopalakrishnan, matric number CE210068. I'm from Group 2. Today I would like to briefly describe our conclusion for the above project. So to make it simple, I will explain the conclusion. So the development temperature control system has achieved success confirmed through the logic analyzer observation of R2 and the PWM outputs. Rigorous testing under various input conditions demonstrated its consistent and precise operation. The system, validated using a logic analyzer, remains inactive until the intended start button is pressed, indicated by the absence of R2 and PWM output signals. The cooler and heater control is achieved through designated ports and binary input values. Following driver specification, the temperature control algorithm demonstrated through software effectively activates cooling or heating elements to maintain water temperature within the desired range. So, meeting its objectives, the project delivers a temperature control system capable of accurate regulation. The integration of ART2 and PWM functionalities enables efficient system monitoring and control, confirmed by the logic analyzer under varying temperature conditions. The system's incorporation of asynchronous serial communication, PWM control, ADC integration, and sensor interfacing enhances functionality and flexibility. So this has resulted in a significant reduction in manual intervention, increased automation, and improved overall efficiency in manufacturing plant operation. So to further enhance reliability and applicability in industrial settings, I can say that in the future we might consider to optimize safety measures as suggested above. The developed temperature control system showcases substantial potential to enhance industrial processes, serving as a successful example of embedded system technology application. So that is all from me.